deep brain stimulation of some of those areas, or at least near those areas. So we already have the technology to put an electrode in that area. I don't think anyone has granted it ethical approval to do it. I think it would need to have a very clear treatment, but certainly there is some work looking at a sort of deep brain stimulation type treatments for depression. I don't know a lot about them. I don't know exactly where they're targeted. It very much depends exactly where you put the electrode, right? So you can have, you know, get in the dopamine centers, yeah, the rat's going to press it all day. You get in a center that causes pain, the rat will press it once and never go there again. And obviously, with human patients, that's something that you really don't want to do. So we have the technology to do it. You know, I think we have enough problems with Facebook without directly letting, you know, giving Mark Zuckerberg control of your dopamine system.
Thank you. I got one more over here, and I see that hand, and I see that hand.
Could you explain the role of dopamine with a gambler that's successful and then a gambler who's not successful?
Right, so you mean for an individual gamble, or do you mean for a lifetime of gambling? A lifetime of gambling. So, yeah, so that's a really interesting one. So first, just at the level of the individual gamble, right? We already saw that. You get the win, you get a spike of dopamine. You get a loss, you get a dip of dopamine. One idea that's out there is that some of this risk-taking that you see in pathological gambling can be explained by, and I can go back to, if I just go back to a slide for a second. If I go back to this slide, so what you can see here, so here's a positive prediction error for reward. This is the win, the gamble that you win. And here's a negative prediction error, here's the gamble that you lose. And what you can see from that, actually, is you can already see there's a slight hiccup with the theory, and that is that the burst you get from winning is more than the dip you get from losing. And one thought, one explanation for why some people develop a pathological gambling or other kinds of risky behaviors is that either they get a bigger burst here and a smaller dip here, or they're just more sensitive to the positive burst than the negative dip, and that will actually drive risk-taking behavior. And there's some evidence for that. My postdoc advisor did some work on that, where they looked at these kinds of prediction errors in humans using fMRI. You can actually measure them in humans, and they saw that people had this sort of bigger response to positive wins, were more likely to take the risk than the people who had the smaller response to positive wins. So that may be one reason why we're getting this sort of risk-taking behavior from a learning perspective. But then also there's the whole baseline tonic dopamine that may tip the balance as well in favor of one or the other. So I think it's probably a combination of two things.
Thanks. We've got another question right here.
Beyond Facebook, I'm just curious what other super egregious abuses of this knowledge that we see in our everyday life. And then also another question, how did you get into this field of study?
Okay, so how do we abuse this knowledge more? And how do, you know, what is already out there that is abusing this knowledge? So one slide that I took out of this talk is actually a course listing at Stanford, which is a course called Behavior Design. And all of the, not all of them, but a lot of the tech guys who come out of Stanford and start these companies, Uber and Snapchat and all the rest of them, actually take this course. It's become like this, this thing that you have to do. And so all of these companies are using this kind of technique, these kinds of techniques, these dopamine bursts, to get us addicted to things, right? So, you know, you'll see it with things like, you know, some apps will have streaks, right? You do something several days in a row, you get more and more rewards, right? But implicit in that, if you break your streak, you get this really big negative prediction error. And that's sort of nudging people to keep engaging with it when they don't want to, you know, don't necessarily want to engage with it. Uber drivers are, you know, sort of encouraged and rewarded to keep doing just one more ride, right? All of these little things to sort of get them to stay on the road. Now, that's the dark side of behavior design, right? So the guy who actually came up with this idea of behavior design, his hope is that actually you can use this kind of thing for good, right? And so you can frame these kinds of things, you know, let's say you can get people to engage in studying more by giving them rewards, right, in some way, right? If you could make I could make my course materials as engaging as Facebook, right? Everyone would get an A all the time, right? So there's definitely, you know, there's some stuff with that, with savings and things like that as well. Some of it relates to dopamine, other parts of it is just more general decision making. So there's definitely a lot of these examples out there already in the world, and there's, you know, more and more of them all the time. So, you know, one more example. Well, here we go. There's an example. I just got 10,000 steps. That's my Fitbit rewarding me for doing it. A prediction error. Another example is in casinos. They will often make wins look like, or losses look like wins. So if you lose and they see you're on a losing streak, they'll come around with a free drink to sort of take the edge off, to try and make this negative prediction error not quite so bad. So there's all these clever tricks they use to make something that looks like you're losing actually look like you're winning, or make it, you know, actually losing, make it look like you're winning. So there's a lot of these things, and they're embedded in the world, and it's kind of scary. It's sort of, you know, Skinner's paradise, right? Skinner envisioned this in the 50s, right? And he thought it would be a utopia. You know, we're sort of very close to creating something like that, where people are being sort of conditioned and rewarded for correct behavior and punished for, you know, not correct behavior. And it's an interesting time we live in. So yes, that's it. So why did I get interested in this kind of stuff? So, you know, like I said, I run the Nerd Lab, and I'm a nerd. So I originally did chemistry as an undergrad, and theoretical chemistry. So, you know, equations, math, and then I decided that the brain was the most interesting thing out there, and I still think that's true. And so this area is one where math actually has a lot to say, and the theory, you know, I sort of hinted at it with these equations, right? With these equations, there's literally equations you can write down for prediction error. There's literally equations you can write down for what tonic dopamine will be doing and how a choice is generated. And you can fit those to behavior, and you can make predictions about how this prediction error is going to affect subsequent behavior. And it's actually pretty good. And so that for me is extremely exciting, because that's, you know, it's like a nerd's dream, right? It's taking the math and actually predicting something, and in this case, human or animal behavior. So that's what's got me in it.
Thank you. I see your hand. I've got another question back here.
I was just wondering if the blinking correlation with tonic dopamine is particular to humans, and secondly, what the possible mechanism behind this kind of thing could be.
Yeah. So no, it's not particular to humans. So the first results actually come from monkeys. The 80s, they gave monkeys these dopamine drugs, and they noticed that, like, so the original observation comes from psychotic patients, where they saw they were blinking like crazy. But then they tested this by giving monkeys these dopamine drugs, and they would see this big, and it's a big effect on blinking. There's some work, I think, that's looked at it in rats as well. I don't know about other animals, so I don't know if it, you know, the dopamine system, I think, is conserved pretty far down. So, you know, I think this could be something that goes all the way down. So, yes, so I think it is across species for sure, certainly across mammals. Does it? Sorry, your second question. Oh, how does it happen? What's the mechanism? So, again, this is something that's not completely perfectly understood. It's thought to be related to the D2 receptors in the striatum. So one thought is that it's, again, this direct and indirect pathways, but now just for blinking. Blinking or not blinking is to some extent a decision, right? It's to some extent a very low-level decision, but it's sort of a decision. And So the thought is that the go pathway that controls blinking is telling you to blink, and the no-go pathway is telling you to not blink. And so the more dopamine you have, the more that no-go pathway is inhibited, the more you blink. That's sort of a very rough guess, but there's a lot more to it to that. And blinking itself turned out to be an extremely interesting phenomenon. So there's some results. Cathy Gottard is at the university here, has found signals of the blink, an efference copy, so a copy of the blink command signal in parts of the brain that really should have nothing to do with blinking, like the amygdala, which is thought to be the fear center, that's the pop site explanation for what the amygdala does. So blinking is actually a very complicated process, and what we're tapping at with this baseline blink rate is what you do when you're at rest. When you are not at rest, when you're talking, you will tend to blink at the punctuation marks of your sentence. When you're reading, you'll tend to blink less, but when you do blink, it's at the end of a paragraph or the end of a sentence. When you're listening to someone, you'll tend to blink when they should punctuate their sentences. So it'd be interesting to compare sort of a grammar Nazi with a non-grammar person, right, to see if they blink differently in those situations. But it really is a very complicated process. So there's a low-level process that seems to do the baseline, but then there's this cognitive process that seems to, it's almost like punctuation. It's passing up the world into different discrete events. And there's even some evidence that you integrate evidence differently that happened before the blink than after the blink. It's like you treat the blink as a punctuation mark in stream of consciousness.
Fascinating. Thank you. Here's another question right up front.
You touched on dopamine's relationship to sleep.
Oh, yeah. So yes. So that was in regard to that first question, or one of the early questions, where the idea would be that if you get lots of sleep, you should replenish your dopamine levels. So dopamine itself is not, I think, directly involved in sleep, but its close cousin norepinephrine is. So norepinephrine is one or two chemical steps away from dopamine. It's very closely related chemically. It has different receptors, different properties, different projection around the brain. So whereas dopamine, if we go back to that brain picture, dopamine projects mainly to the front part of the brain, prefrontal cortex, and the striatum. Norepinephrine, where the main center is actually about here, called the locus ceruleus, tiny thing, 10,000 neurons each side of the brain, that projects everywhere, except striatum, actually everywhere. So the whole of cortex, all cerebellum, it projects down the spinal cord. It's perfect for controlling sleep. When norepinephrine goes off, you fall asleep. When norepinephrine is crazy, you're like super wired. Norepinephrine is in a sweet spot, then you're like perfectly engaged in your task. So norepinephrine is a really interesting cousin. That's another one. And that also amazingly relates to the eyes. So the more norepinephrine you have, the wider your pupils are going to be, which is sort of a really interesting, interesting that you can get all of these sort of very deep structures just from looking at the eyes. So norepinephrine very much is a driver of sleep. When that goes off, you're asleep. But dopamine, less directly so. If you do have elevated levels of tonic dopamine, you will likely be more motivated, but only if you've got the corresponding norepinephrine to keep you awake.
Wow. See that hand going up, and another one here, and another back there. So I'll get you guys in the order that I saw the hand.
Three questions. Now, first, I didn't blink once before I got here, and I'm blinking quite a bit. You get news risk in your people that hear your lectures?
Right. Yeah, okay.
But basically, there's two things that I noticed. One is that on that one you had the three different graphs side by side, the predicted, unpredicted, and unexpected.
Yeah.
So spikes after the stimulation, does that relate anything to programming people to behave a certain way? I mean, like, because when you do the gambling, they have like a lot of flashing lights. Could that be part of a stimulation, expected reward, or?
Oh, you mean sort of after this stuff out here.
No, you're left. Where stimulation pops up, you got that.
Oh,
spike.
this, yes, this stuff that predicts reward. Exactly.
It does match your pleasure sense. Is that true?
So this stuff. So once you've learned that this thing will predict a reward, I can now use this thing as a reward in itself, and I can actually train you to. If I give you another stimulus out here, you'll learn to predict this, and then you'll learn to associate this new stimulus with the reward. So you can sort of go down the chain. It's called second order conditioning. So you can use this now as a reward. And we do this all the time, actually, with money, right? Money is just a piece of paper, but you can, exchange it for goods and services, right? That's the basis of the economy. More primary rewards.
Another thing is that I'm a PTK and honors at Pima College, and I noticed the honor kids that focus on that, they do a lot of crazy classes. They tend to chase scholarships in a crazy way. In the PTK side, we get more into service, and we have a hard time saying no. Does that relate to dopamine, whereas it's a different kind of condition?
That's interesting. I don't know. I mean, it could be, but it may reflect so many other. I mean, especially a decision like that in the real world is going to be so many different factors coming into that that may relate to dopamine risk-taking versus not risk-taking, impulsivity versus not, but may also reflect, just other factors like you have, one kid who's got a lot of time, because maybe they're at home versus one kid who's got no time at all, right? Because they're doing a bunch of other stuff. Maybe they're going to hold down a job. I think there's a lot of other factors. It could be related to dopamine, but I would hesitate to pin it on one source like that. More likely, it's in situations like that, more likely to be social factors that are sort of high-level cognition than affecting high-level cognition than this sort of low-level dopaminergic process. That would be my guess, but one of the issues that we face in, and this I think is a big question for 20th, 21st century neuroscience and psychology is, how the hell does this relate to these kinds of decisions that we're making in real life? And it's a big question right now. There's been a few studies, one looking at self-control, where they took all these self-control tasks that people have done in the laboratory and asked, does it predict self-control in the real world? The answer is not really. And so there's a really big question. Now, I think these tasks are certainly telling us something about gambling and addictive behaviors. There's enough evidence there. But I think when we start to talk about very complicated decisions, we're bringing in processes that we've explicitly isolated and taken out of these kinds of situations. And it's a big question for psychology. Next 10, 20 years, I think, is going to be dominated by that question. Is any of this is relevant, but there's a lot of other stuff going on, especially when you do it in animals. Has it got any relevance for, psychiatric disorders? Yeah. And real-world decision-making as well.
Again, fascinating answer. Here's another question.
First of all, how old are your children?
6, 4, and 2.
So not sort of misleading, changing my question, but
yeah.
In the elementary level, what are they looking at in children? Anything related to everything you're talking about is older.
Yes.
What about younger kids?
That's right. So,
or how does it affect you as a dad?
How does this affect me as a dad? That's a really great question.
Try that one first.
Yeah, so we're just trying to toilet train our 2-year-old. And we had this great idea that maybe we would do it with videos, because he loves videos, the iPad, so we don't normally do the iPad, but, if you sit on the potty, you can get the iPad. And it works. He will sit on the potty if you give him the iPad. The problem is, the minute you take the iPad away, it's a massive negative prediction error, and he goes crazy. Totally freaks out. So we've stopped that. No iPad. Okay, that didn't work. We've moved now to trying to use M&Ms, or little chocolates. Sit on the potty, you get an M&M, get a reward. It's not working either. I think it's, so this, one thing I've learned from this is, it's not easy to train children at all. And these things are complicated as well. And this is actually something that, you know, there's a beautiful paper in the 60s that was written in response to Skinner. So Skinner's idea was, you know, you give things reward and you can train them to do whatever you want. And he even at one point tried to train pigeons to like guide bombs. It's crazy. He thought he could train animals to do anything with reward. And this beautiful paper in the 60s, written by some circus trainers. And they said, no, you can't train an animal to do anything. It's all shaped by what it wants to do and what its natural behaviors are. So you can train a chicken to dance for food. Because a chicken, and what is a chicken dancing? Well, it's a chicken scratching its foot. And that's the natural behavior that they do when they get food. So you can train it to do that. But you can't train a chicken to stand still for food. It's actually impossible to train a chicken to stand still for food. And I think a similar thing is going on in our kids. When we're trying to get them on the potty, is it's just not their, you know, natural behavior. It's not what they're motivated to do. Now, so there is some, you know, I don't know a lot about the full dopamine system in children. Certainly not this prediction error. I would think it would be the same, would be my guess. The tonic system, I think, has higher levels of dopamine in kids. And what that seems to be doing is not necessarily promoting risk-taking per se, like sort of blind risk-taking, but promoting exploration of the world. And this seems to be something that kids are straight up wired to do, is they're curious about the world, and dopamine seems to be a big driver of curiosity. And that's another aspect of the thing, of the work that we're doing in the lab, is what is driving people to explore. And we think this tonic dopamine level might have a role to play. It certainly relates to blink rate. And that is something that I think is the main role of dopamine in children, is really getting them to explore the world and try things and do, you know, random things and learn these crazy connections and how the world works. Because really the only way you ever learn how the world works is getting out there and trying things.
Thank you. And there wasn't here. Another question.
Hi, I was just wondering if there's any research done on dopamine levels in illicit drug use, opioids and marijuana, et cetera.
Yeah, so a lot of those drugs are targeting various aspects of the dopamine system. I'm not a total expert on exactly which drug is targeting which receptor, but the basic idea is most of those drugs are elevating levels of dopamine. That's associated with pleasure. It's also associated with a conditioning response that makes you want more of it. That's very much, very much part of the pathway. Now it's more complicated than that, and the chemistry is much more complicated. And it's not just the dopamine system as well. Norepinephrine is involved, serotonin, these various opioids are involved as well. So it's not just dopamine, but dopamine, as a rule, is getting elevated in most drugs of abuse. When you withdraw, it's getting depressed, right? And more than that, you need more dopamine to sort of to get back to that baseline level. So the sort of regular baseline level that you had before is no longer enough. You need more because you've sort of messed with the system so much. And that's how, with certain drugs of abuse, you see people like Ozzy Osbourne, right, who has Parkinsonian-like symptoms, not because he's got Parkinson's disease, but because he abused drugs for so many years. And that actually was, I think that's, there may be someone who knows this story better than me, but one way they actually started to understand what was going on with Parkinson's was a doctor working in an inner city hospital seeing drug addicts who were shuffling around like Parkinson's patients, but they were 40 years younger because they've been abusing these drugs and knocking out their dopamine system. And I think that is actually part of the story of how we started to understand what was going on with Parkinson's.
Other questions? right here.
I'm not sure if this is completely out of context, but how might fight or flight or threat of violence or fear fit into this framework, or is it outside of it?
It's related, for sure. It's definitely related. So this tonic level of dopamine seems to be related to overall motivation as well, overall motivation to do something. And that's certainly part of the flight or fight decision, right? Is fight or flight. Either one of those, I'm doing something, whether it's run away or or physically fight with someone, versus a freezing response, which would be sort of cowering in a corner trying to hide. So certainly there's an aspect of dopamine that's involved in that. I think that involves not just dopamine. Like many of these behaviors, it's sort of cocktail of neurotransmitters, but also of brain areas. And norepinephrine, I think, is another big one. That will tend to spike when you're in a very stressful situation like that. And that will boost your arousal. So dopamine sort of gets your motivation going to sort of fight or flight. Norepinephrine is boosting your arousal so that you're sort of aware of what's going on around you. But then, you can have a sort of interplay between those, right? So you could have a lot of arousal, but then cowering in the corner. So it's got a part to play in that, but not the only part.
Thank you. Do we have other questions? I'm looking around. I don't right away see any. Right here.
Well, is marijuana specifically known to have any effect on the dopamine system?
I think it does. I'm not an expert on marijuana, or at least not the effect that it has on the brain. I think it does elevate dopamine, but it has, these cannabinoid receptors. It's going through different pathways. So I wouldn't want to say something that's wrong there, but I'm pretty sure it's going to elevate levels of dopamine in addition to many, many other things that it's doing through the more direct effect through these sort of cannabinoid receptors.
Thank you. Oh, another one right here.
How about chocolate?
Well, if you like it and you get it unexpectedly, it's definitely going to boost your dopamine levels. If you don't like it, it's a negative one.
And any other questions out there? I don't see any, which might mean I get to ask a question.
Oh, yeah.
Which is, what effect does exercise have on dopamine levels? And is there a relationship there? I know with Parkinson's, exercise helps a lot.
Yeah, that's a really good one. So definitely, if you elevate your tonic dopamine level, that will get you more invigorated and give you more motivation to go out and do things. My guess is it probably, thinking about these Parkinson's results, probably goes the other way as well. The more you do something, the more you're sort of engaging that dopamine system in motivation and action and motor control. It's got to help. It's got to help.
Very good. Do we have any last question before we wrap it up? I don't see any hands, so thank you so much. Fascinating cafe, fascinating research. And we hope that you all will have a lovely summer and stay cool. And we will see you in the fall. The theme for the Café series downtown here at Magpie's Pizza in fall will be the science of oceans. So we're going to learn about oceans in the fall. So we hope you'll join us in September for that series on oceans, and have a great summer.
We're trying to get the brochure out in time. audiences have watching our diet club will definitely